Good afternoon. We were looking at control schemes for electric drives in the last class. So initially what we had seen was the dynamics in load system, and we said that when we talk about the various operating modes of an electric drive, it could be either starting, transient, or acceleration. This is one of the operating conditions that the drive might encounter. The second one we said was retardation, rather controlled stopping or braking. So this is another typical transient operating condition. The third one could be steady state operation at a particular speed. So when we talked about these three operating conditions, particularly if we are talking about starting, for example, in any motor drive, when the speed is 0, we are going to have the back EMF or induced EMF that is going to be 0. And invariably, when we look at the current that is drawn by the armature or the stator in an induction motor, for example, that is going to be whatever is the applied voltage minus the back EMF divided by whatever is the impedance offered by the motor winding. So if, for example, if we are talking about a DC motor drive, we are going to have IA equal to VA minus EB divided by RA. And EB is going to be 0 when you are starting the drive. That is when the speed is 0. So as a rule, we are going to have this IA value to be very, very large. When IA value is large, then correspondingly, if we try to look at the electromagnetic torque is generally proportional to the product of flux and IA. So you're going to have a very good amount of torque that is being generated for a large value of armature current, provided the flux is a large value. So this is going to allow the drive to accelerate quite fast. So when we want the drive to accelerate really fast, that means we'll have to supply a very large value of IA. But we should ensure that the motor is able to withstand that much of current. The drive unit, what we have as the rectifier or chopper, that is able to supply that much of current. So generally, we might put in a control called current limit control. So this is essentially to ensure that the drive unit or the motor, either of them do not fail because of carrying extremely large current. So when we talk about the starting performance, it is actually a trade-off between how much of time, that is response time of starting, is one of the criteria that we need to look at, along with what is the kind of torque that is being imparted to the load or that is being developed by the motor. So this is one of the criteria. If we actually put in more amount of torque, as per the equation J d omega by dt equal to Te minus TL, if Te happens to be larger, you can have a larger d omega by dt. That means the response time is going to be smaller, or it is going to respond very quickly. The acceleration will be faster. But at the same time, we have to ensure the safety of the drive and motor. What we mean by drive is the power electronic controller that we are using, or the rheostat, or any other type of circuit which we will be using for controlling the amount of current that is being drawn by the motor. So the safety of the drive, the motor drive in general is again another thing that we need to take care of. So both these things will always be at loggerheads. They are not going to be going hand in hand. If I want a very quick response time, if I want the acceleration to be done really, really fast, in that case, I have to develop a large torque. If I have to develop a large torque, then IA will be large. If IA is increased, I have to ensure still the motor is safe. So essentially, it is a trade-off between how much torque is developed, how quickly the motor responds vis-a-vis the safety of the drive itself. So this is very, very typical of kind of requirement which are contradictory to each other. On the one hand, we don't want the commutator to fail. We don't want the sparking to happen in a DC motor drive by drawing excessively large current. But all the same, we want the acceleration to take place quickly, especially considering that our back EMF is going to be 0 during starting. Okay. So this is one thing about starting. The same way when we are talking about braking of a motor drive, you are trying to look at the motor probably running at 1500 RPM or 3000 RPM or something, and then it has to come down to 0 speed in a controlled fashion. So that's what we mean by braking. So when you want this to achieve 0 speed right away, let us say you are in an electric vehicle and you want to avert an accident. So obviously it has to brake as quickly as possible, and 0 speed needs to be reached, needs to be attained as quickly as possible, really quickly. So in which case, you might have to develop a torque in the opposite sense, so that d omega by dt is very, very fast. So this is going to be TE minus TL divided by J. So if I develop a TE also in the reverse sense, if it is a negative torque, then I will have a very fast retardation taking place. So again, to develop a negative torque, large negative torque, I might require a large armature current or stator current. So even in braking performance, if I want actually a very quick response, I might have to push a very large current through the motor drive itself. So this is one of the, again, transient operating conditions where the requirements are contradictory. You want very quick response, but you don't want the motor and drive to get kind of, burnt. So that is again a contradictory requirement. The third kind of operating condition where we want to attain speed control. Okay, so this is where we said that in the last class also we said that if we are talking about, for example, a separately excited DC motor drive or shunt motor drive, we are going to have the characteristic speed torque characteristics somewhat like this. This is how it is going to be. So if I talk about the speed, this is here. And if I talk about the torque, that is along the x-axis. So if we say that we want a particular value of torque to be, supplied by the motor mechanism to the load. So this is the load torque characteristics. If this is the load torque characteristics, if I want the motor to run at this point, if I want this to be the operating point, in that case, I have to ensure that the motor adheres to this kind of operating characteristics. So if I may call this operating characteristics corresponding to V1, and this is probably corresponding to another value of voltage V2, and this is V3, and this is corresponding to V4. So V1 is going to be greater than V2, which is greater than V3, and this is going to be greater than V4. So if it is a 220 motor, 220 volts motor, maybe this is corresponding to 220 volts. And when I want the speed to be decreased to a lower level, which is corresponding to operating point B, then I have to apply probably 180 volts. So V2 corresponds to lower value of voltage. So similarly, I will be able to attain different values of speed at the same value of load torque. The load torque is going to be delivered at the same value, and still the machine will be able to rotate at different speeds. So here I have to effect voltage control. So by effecting voltage control, armature voltage control, I would be able to attain speed control properly. So in general, what I'm trying to get at is we will need control configuration for the drive for three purposes mainly. The first and foremost purpose is to ensure that the drive is safe. So that means protection is one of the major objectives of the control configuration that we are designing for the drive scheme. So that means we have to ensure that the drive unit and the motor are safe. Both of them are safe. That is the first and foremost objective of control configuration, designing a control configuration. The second one is the response time has to be as minimum as possible. So response time needs to be reduced. So if we can really get a very quick response without jeopardizing the safety of the drive, then that is definitely one more thing that we needed to achieve. The third thing is, if I want 1500 RPM, the motor drive should be able to rotate at 1500 RPM irrespective of whatever be the load, whatever be the voltage from the power supply, whatever be the current drawn, I should be able to maintain the speed exactly at the required value. So accuracy of control variables, that is the speed or torque, both have to be maintained at required value. So these are the major three purposes that have to be served by a control scheme that we design for any drive system. So we normally define something called speed regulation for a drive. So the speed regulation for any motor drive is specifically mentioned as what is the no load speed of the motor minus what is the speed at a particular load divided by whatever is the rated speed of the motor. Some people will put no load speed at the bottom, but I would prefer that we put rated speed, because if I am defining a particular motor's uh, nameplate details as 220 volts, 10 ampere, okay, 2 kilowatt, 1200 RPM DC motor. If I say this, what it says is when it is applied with 220 volts and when it is drawing 10 amperes of current delivering 2 kilowatt of power, it will be running at 1200 RPM. So this is the rated speed of the motor. This is the rated speed of the motor. So if I run the same machine at no load, in all probability, it may be running at a higher speed, something like 1300 RPM. This may be the no load speed. So what I want the motor to do is to run at a particular speed, irrespective of the load condition, irrespective of the supply fluctuation, whatever. So in that case, if there is some variation in the speed that is specified by speed regulation, we want to minimize the speed regulation as much as possible so that we are able to achieve a good level of accuracy as far as the speed and torque of the motor are concerned. So the control configuration has to ensure that the speed regulation is minimized as much as possible. So the difference between the no load speed and the speed at any load, that has to be minimized as much as possible so that we are able to maintain the accuracy very well. This is what generally we would like to achieve from the drive configuration. So how do we really go about designing the control loops? So as I told you, the control variable in a drive scheme could be position. So whenever I'm talking about pick and place robo, or if I'm going to talk about a robo in a manufacturing line, or if I am talking about, let us say, gyroscope or telescope or microscope lenses, or CNC machine tools. All these things are going to have position, should be adjustable properly. So it may be a lens position in a gyroscope or telescope or microscope. It is possible that I have to adjust this, or I may be actually adjusting the position of a robotic arm, maybe in a pick and place robo, or I may be talking about a tool adjusted in a lathe. So all these things are typical examples of position control. So if I want the position to be controlled, what I need to do really is, because I'm going to have theta as the position, especially if it is a rotational system, d theta by dt is equal to omega. So if I want to bridge the gap in the position error, or if I have to nullify the position error, this d theta has to be nullified, which will be equal to omega dt. So if I want to nullify the error in the position, then I have to adjust the speed appropriately so that within a specified time interval, I would be able to nullify that error. So invariably, position control loop may be the outermost loop and speed control would be the inner loop. And if I look at the speed, like what I said in the last class, the speed control can be effected based on the equation which is corresponding to J d omega by dt equal to Te minus TL. So by adjusting the torque appropriately, I would be able to bridge the gap in the speed within a specified duration of time. So I should be able to say d omega. If I want to bridge the gap, then I should say whatever is the difference in TE multiplied by, or whatever is the difference in torque, that has to be multiplied by dt. So I'm calling this as the acceleration torque. This is going to be the acceleration torque, which is the difference between electromagnetic torque and the load torque. So this torque control will ensure that the error in the speed is bridged, the gap in the speed is bridged within a specific duration of time. So invariably, the speed control loop will be the inner loop as compared to the position control loop. So if the torque needs to be controlled, now if the torque needs to be controlled, only thing we need to do is specifically to have the current pumped in or flux established appropriately, because in most of the cases, torque is going to be proportional to the product of flux and current. So I have to either control the current or control the flux or control both. So controlling the current is going to affect a change in the torque. So that is going to essentially increase or decrease the torque. So invariably what you would see in many of the position control mechanisms is, if I want a reference position theta, and if I am able to see what is the actual theta that is available with me. So this is the theta actual that is available with me. The difference in the two, whatever I get is the position error. So let me call that as delta theta. So this is going to be the position error. This will be passed through a position controller. This position controller could be a P controller, PI controller, PID controller, fuzzy controller, digital controller, analog controller. In whatever way you want to implement, it can be implemented. So this is the position controller. Now the position controller output will tell me what should be omega star that I need to achieve, or reference speed that I need to achieve, so that the position error can be, nullified. Now, this speed is compared with the actual speed. So this is going to be compared with the actual speed. Once you compare this with the actual speed, what we get here is the error in the speed. So the error in the speed is again now passed through a speed controller. Now the speed controller will actually give me an output as to what kind of torque that I need to develop. So the electromagnetic torque that I need to develop, how much I need to develop over and above the load torque. So I will have a particular value of load torque that needs to be catered to by the electromagnetic torque itself. So this is the load torque, which is a negative value. Now this is the electromagnetic torque reference that I need to develop from the motor side. Now this is going to be the actual electromagnetic torque that is being generated by the motor. Now, whatever is the error in the torque, based on that, I should be able to calculate the current requirement, whether it needs to be increased or decreased, maybe current and flux also. In most of the cases, we may hold the flux as a constant. So current calculation becomes extremely important based on what is the error in the torque. So once you have the current calculation done, now we are going to have again current reference calculation is done, and this needs to be compared with the actual current itself. So this is the actual current that is coming as a feedback. Now this actual current, what I have got here, that will come out of a sensor which is actually sensing the current. Now this is going to go through a current controller or the control circuit. Now this control circuit is going to give out the control signal or firing signal. So what comes out here is the firing signal for the power converter. Now this power converter is going to be connected to the motor drive. So here is the motor, and the motor is coupled to the load. Okay. Now this is connected here. Now from here, we will be sensing what is the kind of current we are getting from the converter into the motor. So we should have a current sensing mechanism here, which I have shown with the help of a red color circle. So this is the current sensing. This is current sensing mechanism. Now, this current sensing mechanism will give me the actual current that is going here, and that will be compared with the reference current. Okay. And similarly, I will have from here, from this particular mechanism, I will have speed and torque sensing. So speed and torque sensing is done here, and that is going to essentially give out what is the actual value of electromagnetic torque. And similarly, I will have what is the actual value of speed that is coming up in the coupling between the motor and the load. So this is the actual speed. Now, if I use an integrator, if I just integrate this actual speed, I should be able to get what is the actual rotor position, because after all, d theta equal to omega dt. So if I integrate omega over time, I should be able to get what is the actual theta. So this happens to be the complete control loop for position control, for a position control mechanism. So this very clearly tells us that the outermost control loop is the position control loop, and the innermost control loop is the current control loop. So hopefully the current control loop should respond much faster because it involves only electrical time constant. Whereas if you look at the speed response, that is going to be slower because this involves mechanical time constant. So the time constant involved here is going to be mechanical time constant, whereas the time constant involved here is going to be only electrical time constant. So generally, the electrical control loop or the current control loop will be executed several times before it gets back to the mechanical control loop or the speed control loop. So you may execute this current control loop 10 or 15 times before you get back to again to check whether the speed error has been nullified or not. So generally, this depends upon, again, the time constants of various system configuration. And this I mentioned in the last class also. The field time constant in a DC motor drive, because it involves a large amount of inductance, this is going to be of the order of tens of millisecond or hundreds of millisecond. Whereas if you try to look at the armature time constant, this is going to be of the order of a few millisecond or less. Whereas if you try to look at the mechanical time constant, this will be of the order of seconds, a few seconds. Whereas if you try to look at, if I am looking at the temperature rise of the drive scheme itself, then the thermal time constant will be of the order of tens of minutes in most of the cases. So this is going to be really, really large. So accordingly, we have to ensure that the execution of the entire control loop is done. For example, for an armature control loop, armature current control loop, it should be done within a few milliseconds. Whereas when we talk about the speed, we have to give it a few seconds before we can see any change in the speed at all. So that is the way it is going to work. Now, if we look at the mechanism corresponding to some of the practically existing loads, if we look at, for example, rolling mills. Rolling mills are basically going to produce sheets of steel, thin sheets of steel. So it will have one roller like this, one set of roller like this, which would be driven by one motor. Then you are going to have another set of roller right next to that, which will have lesser gap than the previous one. Again, this will be driven by another set of motor. And there will be a third roller, which may be again driven by another set of motor. Okay, so we are going to have continuously several sets of rollers, and we are going to pass a sheet of steel through this. So initially we are passing a sheet of steel like this, and it will become thinner and thinner as it comes through the subsequent or consecutive rollers. So it becomes thinner. Because it becomes thinner, obviously, this will become longer. It will be becoming thinner and longer, which means compared to the first set of rollers, which are rotating at a speed of omega 1, the other set of roller, the next set of roller, which is rotating at omega 2, that has to rotate faster because the same sheet of steel, which has now elongated, that has to pass through this further so that no crease is formed. And if I try to look at omega 3, this has to be even faster. So generally, you are going to have omega 1 less than omega 2 less than omega 3 because the length of the sheet of steel, the length of the steel sheet increases and its thickness decreases. So the same volume of steel is pushed through the consecutive rollers. So obviously you are going to see that as the thickness decreases, you are going to have the length increasing. That is why the speed has to increase progressively from here to here. Okay. So which means I might have to set a particular value of reference speed, and based on that, we have to make calculation. So calculate omega 1. And once we calculate omega 1, this may go through a speed control loop for roller 1. So this is roller 1. So I'm going to have this as roller 1. Then this is going to be roller 2. And this is going to be roller 3. So this is going to control the roller 1 speed. Then after that, I'm going to have from omega 1, I might have to put a K factor. So let's say K1 times omega 1, which will actually give me the speed of roller 2. So this is essentially omega star or omega 2 star, what I have got for roller 2. So I have to again have a speed control loop here. Speed control for roller 2. So similarly, I will have another K factor maybe from here further. And I have to calculate what is K2 times omega 2. And then I would be able to calculate what is omega 3 star. So in the case of rolling mill, in the case of printing presses and so on, we might have coordinated control for multiple motor drives which are working together. And similarly, even in textile mill, I may have fibers which are with different colors. All of them need to be fed ultimately to weave a cloth. So I will have generally in textile mill as well as rolling mill and printing presses. I'm giving you some of the typical examples. In all these cases, multi-motor drives will be working, which have to have coordinated control of speed and torque so that the product that comes out ultimately will be properly manufactured rather than having any kind of shortcoming. So in most of the cases, in most of the industrial environments, especially, you are not going to have only one motor working and only one drive unit controlling that one motor. Rather than that, we may have multiple drive units controlling several motors, which all work in a coordinated control format. So that's extremely important when we talk about the control of electric drives. Okay. So if we need to implement all this drive mechanism properly, it is very important to have sensing mechanisms installed properly for all the motor drive. So what all will we be sensing? Obviously, we need to sense the speed and position. These are one of the most important sensing mechanisms that are required in any of the drive scheme. The second thing that we will require, another sensing mechanism we will require, will be for current and voltage. These are also very, very important. And of course, torque sensors. These are also extremely important. So these are some of the sensing mechanisms we commonly use in most of the drive systems. Let's first of all start with speed and position sensing. So for speed sensing, conventionally what we use is a tacho generator. So a tacho generator basically is a permanent magnet DC generator, which would generate very, very small amount of voltage for thousands of RPM. So let us say this is the motor whose speed I want to sense. I'm just going to show it as a cylinder. Okay. To the same shaft, I would have a small tacho generator coupled. So this is going to be the main motor. So this is the main motor whose speed needs to be sensed, and this is going to be the tacho generator. So this is the tacho generator. Now from the tacho generator, I will have two terminals coming out. These are the armature terminals from which I'm going to get the DC voltage. So what comes out of here, this is going to be the voltage, which is the generated voltage from the tacho generator. So this is the generated voltage from the tacho. And if I'm having a permanent magnet put in place, the generated voltage in any DC machine, as you all know, is going to be proportional to the flux and omega. And flux is going to be a fixed value. So this is determined by the permanent magnet's flux. So the permanent magnet is going to offer a constant value of flux no matter what. So the induced EMF, what I have got here as Vg, this is going to be dependent mainly upon the speed. So I may have this as 5 volts per 1000 RPM, or I may have 3 volts per 1500 RPM, something like this. I may have this generator's back EMF constant in such a way that I'm going to have one of these things as the rating of the generator. And please note that this generated voltage is completely isolated from whatever is the armature supply to the motor. So I may be giving this is the VA plus terminal and this is the VA minus terminal for the motor, and that is no way connected to the generated voltage directly. So the major advantage here is VG is isolated from VA. So whatever is the voltage we are getting here, that is isolated and also of a small value. It is going to be of very small magnitude. So mostly I should be able to send it to an electronic circuit without any difficulty, because electronic circuits will be able to handle only a few volts. So I would be able to send this directly to an electronic circuit, which would be, able to diagnose what is the kind of speed at which the system is rotating. So tacho generator is a very neat mechanism for sensing the speed, but only problem is tacho generator itself is a separate generator. This is expensive. This is one of the problems, because it's a DC machine. It is going to be expensive. And another thing is, because it's a machine, that too a DC machine, you are going to have, it's not maintenance free. You have to make sure that it is, maintained on a regular basis. So these are the major two problems. So there are other mechanisms with which you would be able to sense the speed. The second mechanism that we are going to talk about for sensing the speed is an encoder. So encoder is a mechanism which is very, very commonly used in many of the digital control domain, because it is digitally compatible. It is very easily compatible with digital systems. That is the reason why we use an encoder in many of the cases where we are going to directly, feed the speed in the form of a digital output to the control system itself. So what is an encoder? So in an encoder, if I'm going to have the motor again sitting here, this is the main motor. So this is my main motor. And here is the shaft that is coming out of the main motor. So to the shaft, what we are going to do is to attach a disc. So we are going to attach a circular disc to this particular shaft. So in the shaft, we are going to have this disc, which is consisting of small holes along its periphery. So it is going to have holes along its periphery. So this is a hole. Again, I'm going to have holes along its periphery. Now, I can show this disc somewhat like this. This is the disc which is having holes along its periphery like this, all along its complete circumference. Okay. Now, we are going to have on one side of this a source of light, maybe like a bulb or an LED. So I can show an LED instead of a bulb. So let me just show an LED. So this is the disk. And I'm going to have an LED on one side, which is actually emitting light. And on the other side, I'm going to have a photo transistor. So this is the photo transistor on which whose base the light is going to fall. So if this is the disk, I'm going to have the LED on one side, which is going to emit light. And on the other side, I'm going to have a photo transistor. So I can have the photo transistor on the other side like this, in whose base the light is going to be falling. So if I am going to have the LED already connected to some kind of small source, let us say a 5-volt source or something like that. Okay, so this is the 5-volt source which has been connected to the LED. And on the other side, I'm going to have a photo transistor. So this light will fall on the phototransistor's base if the hole is exactly intervening between the LED and the phototransistor. So I am going to have the disk like this. On one side, I'm going to have the LED, and on the other side, I'm going to have the phototransistor. So if a hole is intervening between these two, the LED's light is going to fall on the phototransistor through this hole. If there is a hole intervening, then it will fall on the phototransistor. Now the phototransistor will have a pull-up resistor which may be connected to again 5 volts or 15 volts depending upon whatever is the rating of this particular transistor, and the emitter of this transistor is going to be connected to the ground. Okay, now from here the output will be taken. So what is coming here is the output. Now, whenever the light is falling, this transistor Q will conduct, and because it is conducting, the output will be low. So, when a hole is intervening between the phototransistor, between the LED and the phototransistor, at that instant, output will be low because this resistance will carry a current. This resistance will carry a current because of which the output is going to be low or ground level. Whereas if the hole is not intervening, at that point LED's light will not reach the base of the phototransistor. So when the light is not falling, on the base of the phototransistor, right? This is when the intermediate surface between two holes, something like this. This is the intermediate surface between two holes. So when a hole is not intervening, in that case, we are going to have 15 volts coming up at the output. 15 volts will come up. So if I look at the complete rotation, for example, I will have essentially pulses somewhat like this. It will be 15 volts, 0, 15 volt, 0, and so on. This will be repeating itself. For the entire rotation, if I am going to have, for example, 100 such holes along the periphery, I will have 100 such pulses for one rotation. So for every rotation, I will have as many number of pulses as the number of holes that are carved in this particular disk. So if I count the number of pulses, by counting the number of pulses, we should be able to get the speed of rotation. Able to infer the speed. So for example, if I say that the total number of holes is 50, if I say that if the number of holes in the periphery of the disk equal to 50, and when I count, if I'm going to have 50,000 as the total number of pulses in 1 minute. Okay, then we can say 50,000 divided by 50, which is equal to 1,000. So I can say 1,000 revolutions per minute is the speed of the shaft. So by looking at how many pulses this particular encoder has given out, I should be able to right away get what are the total number of pulses by counting it. And then from that, I should be able to infer what is the speed. If the speed is really, really small, right? In that case, probably it is going to be very, very difficult to get a larger number of count when I'm counting even for a larger time interval. So if the speed is too low, in that case, maybe what we can do is to count a high frequency pulse between two consecutive rising edges or two consecutive falling edges. Between these two, how many high frequency pulses are coming? If I am able to completely get what is the total number of high frequency pulses that are come up between two consecutive rising edges or two consecutive falling edges, I should be able to infer speed quite accurately. For example, if I say that it's a 1 megahertz pulse or 1 kilohertz pulse that is coming between these two, and I'm counting it probably within a matter of 1 millisecond or whatever, then I should be able to say if so many pulses of 1 kilohertz are coming between two consecutive falling edges, and if there are so many holes in the periphery, if there are, let us say, 50 holes again in the periphery, and if I say that between two consecutive rising edges of output pulses, 100 count has been achieved with a 5 kilohertz pulse. So let us say I have a clock or something like that using which I'm emitting 5 kilohertz pulse, and then I'm counting that, and then there are 100 counts that have been achieved. If I just say that, in that case, I should say 100 pulses from 5 kilohertz frequency. So 5 kilohertz frequency pulse, for that, for two consecutive pulses, the time period will be 1 by 5,000 second. So I should say for 100 pulses, it will be 100 by 5,000 seconds. This is the time interval that I must have gotten. So this is for two consecutive pulses. So this will be for 100 such pulses. So if between two holes for crossing from one hole to the next hole, if it is taking 100 by 5000 second, in that case, for one revolution, the shaft should take 50, because there are totally 50 holes, multiplied by 100 divided by 5000. So this is essentially 1 second. So this is going to be 1 revolution per second or 60 revolution per minute. So we should be able to calculate the speed quite accurately if we either use a high frequency pulse and count the number of pulses between two consecutive holes. Or if the speed is really high, then we should be able to calculate the complete revolution per minute by counting the output pulses itself. So the speed sensing can be achieved quite accurately by the encoder mechanism. The last mechanism that I want to talk about, so we looked at tacho generator, then we looked at encoder, which is the second mechanism. The second mechanism, encoder mechanism, is quite accurate and it is digitally compatible because we are going to get the output also in the form of the count of pulses, from which we should be able to calculate directly what is the speed. So what we get as the output is a digital output because we have a counter. The third one, what we can get is, from where we can get the speed, is a resolver. So a resolver mechanism is basically something like this. Let us say I have a disk like this, and the shaft is going to be inserted in the middle like this, because the disk is going to be again attached to the shaft. So here is the motor and here is the shaft, and to the shaft I'm going to attach this disk. The disk is going to be attached here. Now in this disk, I'm going to have multiple concentric circles that are drawn. So I'm going to have one concentric. Let me redraw this because, it has not come out okay. So this is the first circle, which is the shaft. So I'm going to have one concentric circle here. There is a second concentric circle here. And there is going to be a third concentric circle here. So this is the entire disk. Okay. Now I'm going to divide this, for example, into 8 portions. So let me draw one portion like this. This is the second portion. This is the third portion. And this is now divided into 8 portions clearly. Okay. So what I'm going to do is to have an LED here for the last concentric circle and correspondingly a phototransistor. So this is, let us say this is C1, this is C2, and this is C3. So corresponding to C1, I'm going to have one like this. Similarly, corresponding to C2, I'm going to have one more concentric circle. Corresponding to C2, I'm going to have one more LED and phototransistor. And corresponding to C3 also, I'm going to have an LED and a phototransistor. So these are the 3 LED and phototransistor mechanism which I fix corresponding to C1, C2 and C3. So I will have one LED fixed here, which is corresponding to C1. I will have one more LED fixed here, which is corresponding to C2. Then one more fixed here, which is corresponding to C3. Okay. Now, what I'm going to do is to carve out certain portions. For example, in one of them, I may carve out all 3. Okay. So when I carve out all 3, all of them will be essentially transparent. So there will not be any intervening or interruption between the LED and phototransistor. In the second concentric circle, in the second sector, so this is one sector that I am talking about. Now this is the second sector I am talking about. In the second sector, I may not carve out anything from C3, but I would carve out things from C1 and C2. That first two concentric circle I am carving out. Okay. And in the third one, I will carve out material from here, but I will not carve out anything from here. So if I am looking at this particular position of the shaft, I will have the phototransistors giving me output as 0, 0, 0, because all three of them will allow the passage of light of LED onto the phototransistor's base. So this will correspond to 0, 0, 0. Whereas this will correspond to 0, 0, 1, because the third phototransistor would not have allowed, or it would not have gotten the light from the LED, because there is an intervening disk material sitting here which would not have allowed the passage of light. Whereas in the next one, if I try to look at it, this will be 1, 1, 0. The same way I should be able to again carve out, let us say I'm carving out only this portion, and I have not carved out this as well as this. So this is going to be 1, 0, 1. So like that, I should be able to arrange for different sectors, some portions being carved out and some portions not being carved out. And essentially, there are three concentric circles here. So there can be 2 power 3 combinations or 8 combinations right from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, then 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So there can be 8 combinations. 8 combinations are possible. That means I should be able to carve out different combinations of the disk along the 3 concentric circles. So I should be able to differentiate between 0 to 45 degrees as one sector, 45 to 90 degrees as another sector, 90 to 135 degrees as another sector, 135 to how much? 180 degrees as the next sector, and so on. So 360 degrees divided by 2 power 3 will be the resolution that can be obtained using 3 concentric circles. So in general, if there are n concentric circles and n LED phototransistor combination corresponding to each of the concentric circle, then the resolution will be equal to 360 degrees divided by 2 power n. So we should be able to get extremely good resolution as we increase the number of concentric circles further and further. So this will be able to give me directly the shaft position or rotor position. So resolver will be able to give you theta directly. That is, the position can be obtained directly. So if I obtain the position directly, then I should be able to get what is d theta by dt, which is equal to omega. So resolver again is digitally compatible, because what we get directly or the positions of the phototransistor's pulses. It could be either 0 or 1, and we will get the pulses from each of the phototransistor. So in that sense, this would be able to again give a digitally compatible output in the form of rotor position. So encoder, resolver, and the tacho generator are three different mechanisms that can be used for getting the speed. So these can actually be used as speed sensing mechanisms in any of the control systems that can be employed for electric drives. We will look at the current sensing and voltage sensing in electric drives in the next.